on the computer. Okay, I guess we are in business and we can proceed. Okay, so I remind you that last time we discussed a kinetic theory, Boltzmann equation, in the presence of static disorder. So we discussed a metallic sample in the normal phase. So it was a piece of metal, normal phase, and a static disorder inside this sample. And we described the system of electron in the presence of static disorder using Boltzmann equation that says the distribution function of electrons inside the sample is equal to the gradient. Okay, let me be consistent. Gradient with respect to R, with respect to K, and all this is equal to the collision integral, which is an electron disorder collision integral, and that describes scattering processes between electrons and static impurities. And we wrote that from general consideration, the collision integral is always equal to the integral over dk prime. This is a d-dimensional integral. Okay, let me write it slightly more carefully. It's d dk over 2 ph bar in the power t. And here there is a transition probability wkk prime, the probability to have state k occupied and the probability to state k prime empty. This is the incoming part of the flux into the state k minus outgoing part k prime k, fk prime 1 minus fk. Okay, and if wk k prime if is equal to wk prime k, we learn that the collision integral becomes a linear operator minus d-dimensional integral k prime over 2 pi h bar d-dimensional wk k prime f of k minus f of k prime. And this is a linear integral operator. Okay, and we played with it for a little bit, and we found through the formula in the static regime and in the absence of magnetic field. So what we will do today, we will play a little bit more with the same problem, and we will consider AC response, and we also consider finite magnetic fields. And try to understand this equation slightly better. So okay, so let's briefly talk about AC case. So now, instead of a time-independent electric field, let us consider a time-dependent electric field. Still no magnetic field limit. So then Boltzmann equation, right, time-dependent, but position independent, so constant. So it's homogeneous. It's space. It's homogeneous in space. In other words, E is a function of t, but not function of r. Okay, so it means that the gradient in spatial gradient drops, And we have a Boltzmann equation that reads like this. D over dk f is equal to minus integral over dk prime over 2 pi h bar d-dimensional integral wk k prime fk minus fk prime. Okay, so let's assume that electric field is a oscillating field with a single frequency. And therefore we will look for solution delta f as a function of time, which is delta f times ei omega t, which means that upon such function d over dt yields minus I omega, and the equation becomes and we also use an ansatz. So this function delta f, we will parameterize it by part which is a derivative of a Fermi-Dirac distribution function with respect to energy times some function that depends on the angle. And to be in a simple situation, let me consider two-dimensional samples. So in this case, phi would be an angle between the momentum and the direction of electric field. So let me specify d equal 2, and parabolic spectrum E of p is equal to p squared over 2m, to make my life simpler. And then there is only one special vector in the problem. That's the that's the direction of electric field. And then there is a vector of the momentum k and the angle phi, which parameterizes the direction of the momentum with respect to the axis of the electric field. Okay, so that's then the parameterization of the deviation of the distribution function from the equilibrium. Okay, let us plug this into the, plug it into the equation, and we get that equation reads density of states integral over d phi bar prime over 2 pi f of phi minus f of phi prime w phi minus phi prime minus I omega f of phi is equal to minus E times electric field times V Fermi cosine phi. So so in the limit of DC limit, that this term here would drop in the DC limit, in DC limit, where omega is equal to 0, this term drops, and we are back to the usual through the formula we discussed last time. Okay, so remember that in that case we had a solution f of phi was equal to the minus E times electric field V Fermi cosine phi times tau transport. That was the case of omega. That was in the case omega equal to 0. So now let me change it. So omega is no longer equal to 0. And therefore, this is my new solution. And this is something which some unknown function tau of omega that I will plug into this equation, this integral equation. But this function is angle independent. Now, when I plug this solution into the collision integral, I know that what this thing does, when it acts on cosine phi, it just divides. So we know that collision integral, when it acts on cosine phi, it yields cosine phi divided by tau transport. That's with the minus sign, to be careful. And therefore, when we plug this thing into the equation, we get nu minus E V Fermi cosine phi tau of omega divided by tau transport, and change the sign, minus I omega times minus E V Fermi cosine phi times tau, times tau. This was the left-hand side of this equation, and all this is equal to tau of omega. Yeah? And all this is equal to what was on the right-hand side of this equation, minus E V Fermi cosine phi. And now, so they all contain cosine phi in the first harmonic. This drops, they all contain this prefactor, it drops. And therefore, I'm getting the equation, and also and the same goes for V Fermi. It also drops, also drops, also drops. So the equation reads tau of omega divided by tau transport minus plus I omega tau of omega is equal to the minus 1. So it means that tau 1 over tau of omega is equal to 1 over tau transport minus minus 1 over omega is equal to this plus I omega. So tau transport so tau of omega is equal to 1 over tau transport plus I omega is the minus sign. Here minus 1, and it's equal to minus tau transport 1 plus I omega tau transport. Okay, so there's I made some stupid mistake somewhere. It should be a plus sign, of course. We can find it if we really want it, but okay. So this is the replacement that we had. So essentially tau in the equation that for the correction to the distribution function f, we now have a thing that goes like minus df Fermi-Dirac over d energy times minus E cosine phi tau of omega, which now reads df over d epsilon Fermi-Dirac times E cosine phi, and here tau transport divided by 1 plus I omega tau transport. So we see that the only replacement to the distribution function in this part. So where it used to be tau transport, now it has this multiplier, and therefore the time dependent of frequency dependent electric conductivity is a 0 frequency result divided by 1 Okay, I spotted one more mistake. It should be minus here. Sorry. 1 minus I omega tau transport, where sigma at omega equals 0 is just a Drude conductivity, and it's equal to E square times density of states times V Fermi square times tau transport. Okay. So this is a time-dependent electric conductivity. Any questions so far? Is everything clear? Or okay, let's assume that everything is clear. But people, I need to have some response, because I'm not sure to what extent you're following the derivations, and
I'm not sure everything is clear, but I think at this moment I don't have any questions. Maybe I'll ask later.
okay. So in any case, in case you feel you have any questions, you're more than welcome to ask, because without any feedback, it's very difficult to assess the level of understanding. And then I'm not, since on one hand all these things are very well known, on the other hand I don't know to what extent they're known to you.
I'll try to sum up my questions after the class.
Okay.
Come more organized.
Okay, so let us now play with these results a little bit. Try to look at them and understand them from different perspectives. So we solve this problem in the frequency domain. Let us look at this equation in time domain and try to see what it means if we don't do the Fourier transform. So in this case, the deviation of the function from equilibrium is parameterized the function f, which is also a function of time. So if I don't do Fourier transform, so I just keep the time derivative. I'm solving the same problem once again.
What did you define as f?
So f for me is always the parameterization, of distribution function. So I'm using this parameterization. I'm saying my function f of p, r, and t, in this case there's no r dependence, is f Fermi-Dirac of epsilon p plus delta f of p and t, and delta f. So this is the non-equilibrium part of the distribution function. That's the correction to the equilibrium solution to the Fermi-Dirac function as a result of electric field. And then I'm saying that this correction I parameterize as minus df Fermi-Dirac with respect to energy times some function that has an angle dependence on it. And in general has a time dependence in it. So these parameterizations suggest that only electrons in the vicinity of Fermi surface, so if I'm drawing my many-body state, so this is my Fermi surface. I assume that Fermi energy, is much larger than temperature. And then I assume that under the influence of electric field, only a tiny shell in the vicinity of the Fermi surface.
So capital F sets the fluctuations around the Fermi surface?
Not, the fluctuations is a very wrong word here. We will discuss fluctuations later on, but right now there are no fluctuations.
It's like you have the Fermi Dirac, and you have like a small change from the
small
Fermi Dirac.
Deviation from Fermi Dirac, correct?
And the deviation amplitude is set by this.
So deviation,
but it's time dependent and angle dependent.
Exactly. So it's very important. It's very important. It's very important that we are considering angle dependent deviation from the Fermi surface, because deviations that are angle independent will give rise to no current. Is this statement absolutely clear?
Okay.
Or not?
Okay.
I guess it's not clear.
I said it's okay.
Okay. So that's why we are looking after the angle dependent correction to the distribution function. Only angle dependent part of the distribution function will give rise to a finite current. And therefore, angle dependence is absolutely crucial here. Now, if electric field is time independent, that's the only thing that we have here. But if electric field is time dependent, we need to include time dependence in the parameterization F. So in other words, the deviation of distribution function from Fermi-Dirac type equilibrium is also time dependent. So you apply a time dependent electric field, and roughly speaking, so you have a Fermi surface, you apply electric field, and electric field pushes Fermi surface into that direction or that direction, and it oscillates in time. So it deforms Fermi surface one way or another. It tries to create more electrons that move into the direction of the electric field applied than in the direction where electric field, which is opposite to where it's applied. Okay? So in a way, so there is a driving force here that tries to move the electrons into the direction of the driving force. And there is a resistance to this driving force. Where the resistance to the driving force is coming from? Why the Fermi surface is not just moving all the way to the right? Imagine that you apply the electric field that points to the right. So what would happen to the electrons if there would be no disorder? Let me ask this basic question. What would happen to the Fermi surface if we apply electric field and there's no disorder?
So I think it will stretch because you accelerate electrons, and if there is no disorder, you can kind of occupy more and more states in K-space. So, well,
let us look. So we have an equation. So Newton's equation will tell us dp over dt is equal to E times E, right? That's the semiclassical equation of motion in the absence of any disorder. What is the solution of this equation? The solution of this equation, P as a function of t, is P at that t equals 0 plus E times t. T is a time. So it means that the component of the momentum, which is parallel to electric field, is linearly growing in time. And the component of the momentum, which is perpendicular to electric field, is unchanged. Do you agree? Say something. Agree, disagree?
Yes, we agree.
Okay, then let's have a circle. These are the states with the momentum that are filled in. Now let's take a particular state inside the surface. So let's have a state with the momentum which corresponds to this blue dot. And let's point electric field into this direction and call this direction X. Then the momentum of the blue dot has two components. This is Px and this is Py. Okay, this is X and Y. So what happens to the component Py as time goes?
Nothing.
Nothing. What happens with the component Px as time goes?
It increases.
It increases. So it means that after time passes, this blue dot will move to here, schematically. What happens with, I don't know, with another point? Let's choose another point. Let's pick a green point inside the Fermi surface and wait the same amount of time. So what would happen to this point after the same amount of time t? Where it will move?
Well, it will.
Shouldn't it move to the right?
It will move to the right. By what amount?
By E times time.
So yeah. So the green point will also move by E times. So if we wait time dt, so the green point moves in X direction by E times dt. And the blue point, by what amount it moves?
The same amount.
The same amount. So each and every point.
It conserves the shape.
Yes, so each and every point moves into the X direction by the same amount. So it means that the entire circle moves, and keeping its shape, it moves by the same amount to the right. So if it would be no impurities, then what would happen with the Fermi surface? It will keep moving at constant velocity to the right, namely into the direction of the electric field. That's all there is if there are no impurities. Now, when we solved Boltzmann equation and DC limit, we found the solution is time independent. So what it means that in the presence of the impurities, the Fermi surface is not moving to the right. So there are two forces that act in the opposite direction. There is a force of electric field which tries to move the Fermi surface all the way to the right at a constant speed. And there is a process which is called relaxation that comes from elastic impurities, that results from the scattering from the elastic impurities. And what it does absolutely opposite. It shows that if you have more electrons that move to the right, that electrons move to the left. So what scattering does, it scatters electrons from the overpopulated areas of distribution, and it scatters it back to where there's a lack of electrons. And this results in the distortion of the shape of the Fermi surface. So instead of looking like a sphere, the Fermi surface in the presence of the impurity reaches a situation when it's not a sphere, but it has more electrons into the direction of electric field than into the direction which is opposite to the electric field. And this is precisely this term is harmonic phi, cosine phi. So when phi is equal to 0, this thing is in the direction of electric field and it's positive. When phi is equal to pi, it's negative. So there are less electrons here and more electrons here. So we have an extra electrons here and lack of electrons there. And that's the change of the Fermi surface that results due to the competition between scattering by static impurities and a driving electric field. Note that if you would look at the direction which is perpendicular to the electric field, oops, bytes keep disappearing. If you look at this direction, then we will see no change because it will be angle pi over 2, and in this direction electric field does nothing. So that was the story about competition between the driving field and impurities. One is pushing distribution to the right, another is restoring it to the left. Now, what happens when we include a time-dependent electric field at a given frequency? That the function, that parameter, and we see here there is only one harmonic that emerges, and this is cosine phi. This is the lowest harmonics, which is angle dependent. Okay, so this is an angle dependent part, and it's absolutely crucial to keep this angle dependence. Now, if we are going back to our equation, now we include some time dependence in it, and therefore function f as a function of angle and time has explicit time dependence. So let's take this solution, this ansatz, and plug it into the time-dependent Boltzmann equation. So I'm writing it from the beginning just to have all nodes at the same place. So in terms of this function, in terms of function f capital, I have a part which is a time-dependent part plus density of states integral over phi prime over 2 pi f of phi n t minus f of phi prime and t times w phi minus phi prime is equal to minus E times electric field as a function of time, V Fermi cosine phi. And we have already solved this equation by Fourier transform a few minutes ago. Let's do something else instead. We plug the ansatz f as a function of phi and t, something which is almost obvious, times a function of time. Now, when we look at this equation, we realize that collision integral is an operator that acts on the angular part, but doesn't act on the time, which is time dependent. So this, from the point of view of collision integral, is just a trivial operator, just a trivial multiplicative factor. And therefore, the only part on which collision integral acts is the cosine phi. But we know how collision integral acts on the part which is a cosine phi. It yields a transport time. So the equation, if we plug this f in this form into equation above, we get df as a derivative with respect to time plus 1 over tau transport f as a function of time. I'm only keeping this part, is equal to the electric field as a function of time. I canceled all the parts which are proportional to electric field and cosine phi. So this is just the equation for time-dependent part of the distribution function. That's a very simple linear equation. We all know how to solve it. And the solution reads f of t is equal to integral from minus infinity to t dt prime e minus t prime divided by tau transport e of t prime and now current that flows into the system as a time-dependent thing, and it's equal to minus E times density of states times V Fermi integral d phi from 0 to 2 pi cosine phi times f of phi and t. And f of phi and t, see above. So I plug it in and I get that this thing is equal to E squared times density of states times V Fermi square over 2 integral from minus infinity to t dt prime E minus t prime divided by tau transport E t prime. Now this object in front of the integral, identify, and I know this is my just drew the conductivity, or sigma 0 is just E square nu V Fermi square over 2. Now, if I look at this equation, so what did I get here? I get a linear equation between current at the time t and electric field at the time t prime. So this is what is called linear response relation. So what this equation tells me, that current at the time t is some integral from minus infinity to t dt prime sigma t minus t prime times E of a t prime. And this is time dependent response function. So what is this sigma of t? Sigma of t, I read it from the equation above, it's sigma 0 times E minus T over tau transport. Or explicitly E square nu V Fermi square over 2 E sorry, I made a mistake. Sorry, I made a mistake. This is not sigma 0. I'm sorry, I got confused. This is a wrong statement. I take it back. I take this back. It's E square nu V Fermi over 2 E minus T over tau transport. So if we look back at this relation, and we write it explicitly, J of T is equal to E square nu V Fermi square over 2 integral from minus 0 to T dt prime E minus T prime over tau transport E of T prime, that this object inside the integral is frequently called memory function. So it shows how fast the current at the time t decays due to response at the time t prime. Now, if electric field is time independent, then, so in the limit electric field is time independent, that this integral, then if electric field as a function of time is just a constant, then the integral from minus infinity to t dt prime E minus t prime divided by tau transport yields tau transport. And we are back to the DC electric conductivity. Okay.
Can you repeat the last point?
Okay, so the last point is if electric field is time independent. So if we go into DC limit, where frequency of electric field goes to 0, yeah? So we always think about electric field as a function of time, as some electric field times E in the power I omega t. Now in the limit, omega goes to 0, this thing goes into just a constant. Yeah?
Okay.
Then the current that I computed as a function of time is now E square times density of states times V Fermi square divided by 2 integral from minus infinity to t dt prime E in the power minus t prime divided by tau times E. Then I take this E outside of the integral, it would be E square nu V Fermi square over 2 times electric field times integral from minus infinity till t dt prime E in the power minus t prime divided by tau. Now I can shift tau prime by t. That we call t minus t prime, a new variable. What was not used? I don't know. T1. Let me denote it as T1. Then integral from minus infinity till t dt prime e in the power minus t minus t prime divided by tau transport. Sorry, forget to write transport. Transport is just an integral over dt1 from minus infinity. Sorry, when t prime is when t prime, it's an integral. Sorry, it's integral from 0 to plus infinity at the with a minus sign e in the power t1 minus over tau transport. And this object will be equal to tau transport e in the power minus t1 over tau transport between 0 and infinity. And this gives me tau transport. And I screw up the sign, but this integral is positive, so the answer should be positive.
Yes, okay.
Okay, so therefore, in the DC limit, I'm recovering the familiar result that the current is equal to E square nu V Fermi square over 2 tau transport times electric field. And all these things we called electric conductivity at frequency goes to 0. So it's the same equation. It's the same equation. Just in the time domain, and we see that in the case of time-dependent electric field, conductivity is a time-dependent function, which looks like E square nu V Fermi square over 2 E in the power minus t over tau. That's the time-dependent response. That case, and in the frequency space, the same linear response coefficient is just a Fourier transform from 0 to infinity e in the power I omega t sigma of t. And if you plug this in, you get that this thing is equal to sigma 0, 1 minus I omega tau. So there are two complementary ways of looking at this problem, one in the frequency space, another in the time representation. And there is a single response coefficient sigma that in the time representation exponentially decaying function of tau on the scale tau transport, or in a frequency representation, it's again a function that has a pole as a function of frequency. It has a pole when this condition is satisfied. So it means that minus I omega is equal to minus 1 divided by tau transport. So there's a pole that omega is equal to minus I over tau transport. So as a function of frequency, there is this function has a function of complex frequency. There is a pole at the, there is a pole here. That was wrong. There's a pole here at the point minus y over tau transport. So this is a response coefficient that has a single pole as a function of frequency in the complex plane at that point. That's its analytic structure of as a function of frequency, a single pole in the lower half plane at this point. And if you look at this function in time representation, that's its exponentially decaying function with this typical scale, which is a transfer time. Any questions? Okay, so if everything seems to be so clear, let us proceed. So we just found this function. We just found this function using Boltzmann equation. Now, what are alternative ways of obtaining this result? And of course, the alternative derivation of this thing would be by using Kuba formula. Kuba form 4. Now, normally, Kuba approach is a microscopic approach based on many body formalism. However, and this is something that I like to show now, in this particular case, there is a very simple version of Kuba response. So this is something which is called classical Kuba formula. So what is the classical version of Kuba? How many of you ever heard of Kuba formula, or Kuba approach?
I have heard.
Anybody else?
I don't, I'm not familiar with it.
Okay. What about other people? They keep silent.
I didn't hear of it.
Okay, so people didn't hear about. Okay, good. So then for you, it would be a first time ever you learn about Kuba approach. And for the sake of this course, I will not go into the justification or explanation. It's a very powerful thing, but let me present it at the most simple version of this approach, tailored for this problem in particular. But I think it will give you some spirit of what Kuba approach is and how it works. So what is the idea of Kuba approach? The main idea, so we are interested in some response coefficient. In this particular case, it's electric conductivity. So what it means, what it means that we have a current, in this case, electric current that flows into the direction of electric field, and it's equal by response function or in the Fourier representation, current at frequency omega is equal to the conductivity on frequency omega times electric field at the same frequency. This is the response function. So how it works, you have a circuit, you apply electric field, time-dependent electric field to this circuit, and you measure current that flows through the circuit. So this is a typical linear response measurement. There is a small perturbation that drives the system out of equilibrium, and you this is E, and you measure something that flows through the system as a response of this driving force E, and the coefficient of proportionality, it's a linear response coefficient. Now there is a statement, and this statement will be absolutely general for any quantity that has a linear response, that you can find this coefficient if you study the correlation of fluctuation of this object J in the absence of electric field. So it goes like this. Let us now switch electric field off. In the same circuit that we consider above, we switch the electric field off. And consider the situation of thermal equilibrium. Then the statement is, let us measure fluctuations of current in this circuit that flow there purely at thermal equilibrium. So instead of computing the response function to the external electric field E, I will consider a fluctuations of currents that flow in the system. And the statement is that this object is proportional to electric conductivity. So I don't need, I have two complementary ways of looking at the problem to turn on the electric field and compute the response, or I don't turn the electric field and I consider the correlation function of currents, or more carefully, in this case, I need to compute the correlation function of velocity operators. So if I'm interested in the conductivity component into X direction, I take a velocity operator in X direction and velocity operator at the same direction, and I compute the response function. In general, it's a tensor, and if this is alpha and beta, that would be alpha and beta component. But if we discuss longitudinal conductivity, namely the response of current that flows in the same direction than the electric field, and we think that electric field is directed into X direction, then that conductivity, which is longitudinal, it will be E squared times nu, Vx at the time t, Vx at the time 0. So I relate the response function to the correlation function of velocity operator. Now, this is a very general formalism, not necessarily classical. It's usually maybe it's too strong a word. It also holds in quantum mechanics. In that case, these are quantum mechanical operators, but in the simplest form, if you're interested in the response in the electric current, you just consider the correlation function of these operators. So how does it work in this approach? So let us look at the particle, and let us believe that at the moment t equal to 0, we have created a particle with a single particle that has a velocity in some direction. So our distribution function has an addition of a particle that at t equals 0 just flies in some direction that we will parameterize by angle phi 0. Okay, then let us plug this thing into the Boltzmann equation. We get the following equation in time. Times W phi minus phi prime equal to 0. So essentially, I'm saying that the correlation function satisfies the same equation as distribution function. Then my correlation function, then function f as a function of phi and t, can be represented in terms of various harmonics as a sum of cosine and phi f n. In principle also things that are odd harmonics. This will be symmetric and anti-symmetric harmonics. These guys are functions of time. I plug this back to the equation and I get that lowest harmonics satisfy the same equation we have already seen. Which means that phi 1 as a function of time is equal to phi 1 at t equals 0 e minus t over tau transport. And this guy is just cosine phi 0. Therefore, Vx at the time 0 times Vx at the time t will be equal to the V Fermi square integral over d phi 0 over 2 pi cosine square of phi 0 e minus t over tau transport. And therefore it will be equal to V Fermi square over 2 e minus t over tau transport. So this is the response of the velocity operator. And electric conductivity would be equal to E square times density of states times the response function of the velocity operator. So the message of this story, you may or may not include electric field into the Boltzmann equation. You can either include it and compute linear response, or you can compute classical velocity correlation function and use Kubo formula to extract the electric conductivity. Kubo formula is something which goes way beyond a classical limit. It's actually a fully quantum mechanical theory and can be just exact in computation of linear response coefficients. Okay. Any questions about this point?
Can you go up a little bit? I need to complete my notes.
Okay.
Okay, thank you.
Can you please upload the notes as well?
Yes, I'll upload the notes.
Thank you very much.
Okay. Now, let us describe let us discuss last point of the same problem, and then we'll proceed to magnetic resistivity. So one last comment, it's so-called tau approximation. Tau approximation. So like I said, collision integral, so thermal electric conductivity, so electric conductivity is a result of two processes. There's a tug of war between two processes, a pushing electric field and restoring scattering processes. Now, and strictly speaking, scattering processes are described by collision operator, which is a linear or non-linear, depending on whether W k k prime is equal to W k prime k. But even if this thing is satisfied, then it's a linear, that's a linear operator. So linear integral operator. Okay, let me just write it once again. So it's an operator dk prime. It's a d-dimensional integral over 2 pi h bar k at W k k prime f of k minus f of k prime. So this is a linear integral equation. Of course, it's solvable. However, it's an integral equation, so it's not always easy to solve it. What people frequently do is to use so-called tau approximation. So what they say, let's replace this kernel by its diagonal part. So we have W k k prime. So this operator, sorry, I take my word back. So if this operator is linear, let me think about it as some linear kernel k prime acting on f k prime and sum over d k prime. And this defines me the kernel I k k prime, which is, if I look at this equation, then I k prime is equal to the, just a sec, so let me compare these two objects. So I acting on f, it's equal to the integral of dk prime W k k prime acting on f k prime minus f of k integral over dk prime W k k prime. And okay, then I can say that this thing is an action of thinking. I want to replace this thing by a kernel and read from here the definition of this matrix. So it's W k prime minus delta function of k and k prime divided by tau, where 1 over tau is an integral over dk prime f k prime, and this depends in general on k. So So it means there is an integral equation. I can look at this integral equation, and so there's a linear operator with some matrix that represents this operator, I, K, K prime. Now, and this matrix, of course, has a part which is diagonal in the K, K prime representation, and there's a part which is in general non-diagonal. That's the matrix. So in many cases, in order to estimate rather than computing things carefully with coefficients, it's sufficient to replace the whole thing by its diagonal part and just forget about a non-diagonal part of collision integral. It's not a control approximation, but very frequently it's good enough to estimate things up to numerical coefficients or just to estimate scales. So in this case, one replaces the collision integral as a linear operator by its diagonal part, in which case this thing becomes just a very simple term. And then instead of solving Boltzmann equation, which is integral complicated equation, one uses an effective replacement of collision integral by its diagonal part. So essentially now it's a matrix in K prime, where you have only elements on the diagonal, and these elements are 1 over tau K. And if you will do this approximation and go back to the analysis we performed today and last time, you will see that this yields the correct result even for a parabolic spectrum and especially homogeneous electric field, even with the correct numerical coefficients. In a more complicated situation, for example, when Fermi surface is not a parabolic spectrum, but it's a complicated, I don't know, has many pockets in the phase space of complicated spectrum, electric field, which is inhomogeneous. This approximation, of course, will not give you the correct results up to the numerical coefficients. However, it's good enough to estimate scales in many cases. So what this approximation tells you is that for any particle with the momentum K, there is a relaxation process, says, as a result of impurity scattering. And therefore there is a part in the equation that tries to bring system back to the equilibrium. This is the equilibrium solution at the rate 1 over tau transport. So this is the simplest approximation you can do to Boltzmann equation if you want to extract typical scales and see how it comes about. Okay. This is what's called tau approximation. Now the next thing we can do with Boltzmann equation is to study magnetoconductivity. So what is magnetoconductivity? It's the dependence of electric conductivity on the external magnetic field. So in addition to the electric field, which drives the system out of equilibrium, there is a magnetic field. And for our purposes, we will only discuss magnetic field, which is time independent. So the picture is like that. There is a two-dimensional sample. There's x-axis, y-axis, and z-axis. And there's an electric field that has an x component. So electric field is in this direction. And there is a magnetic field which is parallel to z component. So let's assume that E is parallel to x and B is parallel to z. And let's decide that the sample is two-dimensional sample. So it can be a metallic film, two-dimensional metallic film. And the goal is to compute electric conductivity in the presence of magnetic field. Once again, the same story we discuss all over again and again. So there is a sample, there are some random impurities in this sample. And now we want to compute electric conductivity, but also account for the magnetic field. Now, why magnetic field is important? What magnetic field does? Why we want to account for this field? Any ideas?
What is the question? Like what a magnetic field does generally?
Why do we want to include magnetic field in our treatment? Why magnetic field? Why, I don't know, not gravitational fields?
Well, it applies a Lorentz force.
Yes, it applies, it creates Lorentz force. And what does Lorentz force do?
Like a rotation maybe?
Yes. So if you have a magnetic field applied into z direction,
Like a rotation around the z-axis.
yeah. So let's consider case where there's no impurities whatsoever. So there is a two-dimensional sample, and there is a perpendicular to it magnetic field. And then there is an electron with the momentum p that in the absence of magnetic field will just go in space along the straight line. What will it do in the presence of magnetic field? What will happen to its motion?
Go up in the x-axis?
So it's a two-dimensional sample, yeah? So there is no motion in z direction, yeah?
No, up in the x direction.
So, okay, so there is x, and there is y, and there's a magnetic field. So you think that he will move in that direction?
No, I think it's the other. I think it's the opposite direction. Like
Into that direction?
I think, but I need to.
Okay, so let's remind ourselves what.
I forgot which hand you use for the.
Okay, so the equation reads that if we have a force that dp over dt is equal to E times E plus minus E over C V cross B. And in the case of parabolic spectrum, minus E over M C P cross B, where I assume that Vp is grad P of epsilon P, grad P over P square over 2M, which means P over M. Okay, so that's the semi-classical equation of motion. Now, assume that there is no electric field, assume that electric field is 0. Then the equation of motion reads dp over dt is equal to minus E over mc P cross B. Now let's discuss what is P cross B. So P cross B is x, y, z, bx, by, bz, px, py, pz. Now we decided that this guy, that bx is equal to by is equal to 0 because it's a two-dimensional metallic film, and magnetic field is applied into z direction, so there is no x and y component. Moreover, we decided it's a two-dimensional film, so there is only x and y components of the velocity, so pz is equal to 0. So this object reads x, y, and z, 0, 0, bz, px, py, and 0. So there's only one component here, which means bz times x py minus y px. So the equation of motion reads dp with respect to t is equal to minus e over c. Let me look again. Minus e over mc. What was that? The p cross b is this guy. bx times x, and the component py are minus bx times y and component px. So dp dt is equal to minus e bx over mc py times vector in the x direction minus px times vector in the y direction. So if I project this equation onto x and y component, then dpx with respect to dt will be equal to minus ebx over mc py, dpy with respect to dt will be equal to ebx over mc px. Okay, so this is the equation. Now we can try to solve this equation. So what is the solution of this equation? The solution is obvious, and it tells that px is equal to some p cosine omega t, py is p sine omega t. So let's plug it in. So the first equation reads minus p times omega sinus omega t is equal to minus eb over mc p sinus omega t. And the second equation reads p omega cosinus omega t is equal to eb over mc p cosinus omega t. So this is my system of equation, and first one tells me p is gone, omega is equal to eb over omega c, because I can cross this and I can cross this. And the second equation also tells me exactly the same. And therefore, this is my solution. And I will call the object, I will call this object omega cyclotron, EB over MC. So PX and PY are functions that are oscillating functions with respect to time. So if I draw my PX and PY, what it will do, it will perform an oscillatory motion on the plane px/py. The momentum of my particle will rotate at a frequency which is called cyclotron frequency, EB over MC. Do you agree? Is this picture clear, people? Because I don't know whether it is or it's not.
I think I got it, but I kind of lost you at the end because I wasn't very concentrated.
So I just taken, so these are two very simple equations, and I'm guessing the solution. So I'm
Yeah, the calculations, I think, are clear, but just the drawing didn't get what you said.
So the momentum oscillates. So the momentum.
Yes, yes.
So,
it goes around the circle.
So momentum goes around on the circle. Yeah. So there's a finite p, and the momentum. So the absolute value of the momentum is fixed,
Okay.
because the energy is conserved. Yeah. Magnetic field cannot change the energy.
Yes.
So what happens that there is a vector of the momentum. It points in some direction, and this direction changes all the time.
Yeah.
So that's what the momentum does.
Okay.
Okay, the absolute value of the momentum is fixed because p square over 2m is equal to energy, and this is fixed. Now the next question to ask, what does it mean about trajectory of the particle in the real space? So we know that r dot is equal to velocity, and this is equal to p over m for the case of parabolic spectrum. So it means that x dot is equal to 1 over m px, and y dot is equal to 1 over m py. But this object we have already computed, and this is equal to the cosine omega t, and this is equal to 1 over m sine omega t. Right? That was our. So what it tells us about x and y as a function of t. So we now need to solve an equation dx as a function of t. Derivative with respect to t is equal to 1 over m cosine omega t. The solution of this equation is, of course, x of t is equal to minus 1 over m omega sine omega t plus x0. If I differentiate these things, sorry, plus. If I differentiate this thing, I get back the equation above, and the same y of t, it's 1 over m omega cosine omega t, this time with minus, plus y0. So this describes us again a point. So if I look at it as x minus x0, it's equal to 1 over m omega sine omega t, yt minus y0 is equal to 1 over m omega cosine omega t. So I see that x t minus x0 square plus yt minus y0 square is always equal to 1 over m omega square, and what this is just equal to 1 over m, and we said that omega c is was eb over mc, So we get that it's equal to C over EB squared. So it's essentially rotation on the circle with the radius of the circle being C over EB. So what electron does, or the particle does, it rotates around its equilibrium position on a radius with this length, and if magnetic field goes to 0, then this radius diverges and we go back to the solution, which is a straight line. Okay? But if there's a finite magnetic field, then the particle does not go anywhere. It performs circular motion. Okay? That's what happens in the absence of the electric field. Now, this is the classical.
So R goes to infinity means that P doesn't rotate.
I couldn't hear you. Say it again.
I say that maybe you can look at R goes to infinity like P doesn't rotate if it can't complete a circle. Like,
Yeah, but that's a very big circle.
yes, I mean that now when R is a constant, P goes through the circle, but if R goes to infinity, P is relatively constant relative to the big circle.
Okay, so now we need to do two things. We need to include electric field and we need to include disorder. So people, I suggest us to make, I don't know, 5 minutes break. Let's reconvene here at 5:45, 5:45, and continue continue this discussion, okay? Just let's make a quick break. I need to get coffee and we'll proceed. together. Шама? Если мастер ки. יש לי מאסטר כי המפתח שלי, אני לא חושב שיעבוד, אבל אחד משניהם, לבן או ירוק. אני חושב שאחד מהם אמור לעבוד. אוקיי. What do you mean? Estimate the magnitude of this radius in a real system. You mean for a given magnetic field? What is the typical cyclotron radius? It depends on the field, yeah? What is the so the mass of electron is known. Mass of electron is known. Speed of light is known. Now the question is, how strong is the magnetic field? Now I don't remember the typical values off the top of my hand, but typically it would be, I mean, for metallic systems that I know, it would be typically nanometers. Well, it depends on how strong is the magnetic field, yeah? So if magnetic field is very strong, this thing is very small. So it's inversely proportional to the magnetic field. We can, but just not in the real time, but if magnetic field is large, then it's small, then it's very large. If it's large, then it's very small. Now, so are we all back? Seems that some people are not there, not here yet. Okay, so quantum Hall regime. Few Tesla. Good. So let's put few Tesla. Okay, it's a good question. I think for few Tesla it will be nanometers. Cyclotron radius, but a word of caution, all what I'm saying is completely inapplicable in the quantum Hall regime. So all what I'm saying assumes the validity of semi-classical approximation. I did not stress this point, which puts a very strong bound on how large the magnetic field can be. And we definitely cannot approach quantum Hall effect using this way of reasoning. So our description fails way before we reach quantum Hall. It will hold, of course, for classical Hall effect. But we will discuss the validity of all this approximation and where this semi-classical treatment breaks down and what should we do, how to improve it. It's a very simplified way of looking at electrons, and we assume that the spectrum is continuous, for example, yeah, and it's not quantized at all. So I'm just thinking in terms of classical equations of motions, in terms of classical particles. Now, if the spectrum is quantized, like in a quantum Hall effect, then of course, it's no longer k squared over 2m. Yeah, it's a discrete quantized levels of quantum Hall. So all this breaks down well before that. But it's a good question. Yeah, we can of course estimate it for physically feasible magnetic fields and see what is the typical size. Okay, so now since time is running short, let me just include electric field in the Boltzmann equation and compute the resulting magnetic conductivity, which will be a classical Hall effect for a very simple spectrum. So two-dimensional case, p square over 2m spectrum, the same story again and again. So we are looking at the term V cross B times grad K acting on distribution function. That the term we need to add to the, okay, let me start from the beginning. Let me be more systematic, sorry. So Boltzmann equation, df over dt plus V grad F, this is the grad in the real space, minus E over C V cross B grad in the K space of distribution function minus E over C, sorry, what I'm getting tight, sorry, minus E times E grad K acting on distribution function. That's the part that's coming from the electric field, and all this is equal to the collision integral. Now linear response approach, which means that here I'm writing Fermi-Dirac function because this term is linear with respect to the electric field, and I'm getting an equation d over dt plus V grad in the real space minus E over C V cross B grad K minus collision integral acting on F. All this is equal to the E times electric field times gradient K acting on F Fermi-Dirac epsilon K. Now V cross B times gradient K acting on F, I can write in a polar coordinates. So B so I need to write gradient of K in polar coordinates, and there'll be a part which is in the direction of K, and there will be a part, so it's a two-dimensional gradient operator. That's K vector. That's an angle phi. So there is a component which is proportional to the, in the direction of phi, and there is a component in the direction of K, which is parallel, which is the same direction, which is parallel to the direction V of K. So things that are proportional to the direction of V of K, so product V of K times V cross B will be equal to 0, because V cross B is orthogonal to V, and therefore part which is parallel to K will vanish. So the only thing that will survive from grad of K will be in the direction which is direction of the angle. So I can write V cross B gradient K acting on F. It's V cross B times V df over d epsilon k minus b over m df over d phi k, and this part, as we said, is 0. So just a simple representation of gradient in polar coordinates, and notion that velocity is k, that velocity is k over m. So once you substitute this, you will see that this term simplifies into the result that I wrote. And therefore, if we now write distribution function is equal some equilibrium part plus delta f, then the Boltzmann equation reads d over dt plus v grad r minus e b over mc d over d phi acting on f, on delta f, plus collision integral acting on delta f. All these just is equal to e v Fermi cosine phi df0 d Fermi Dirac over d epsilon k. Okay, so the only new addition to the Boltzmann equation is this term that came with magnetic field. The same ansatz as many times before, minus df0 respect to d epsilon k times some unknown function that contains angular direction, angular dependence, sorry. And for this function, we get omega c d over d phi acting on f minus collision integral acting on this function is equal to minus e, equal to minus electric field times v times cosine phi. I might be missing electric charge. I don't see it right now, but maybe it's okay. Where omega c is equal to eb. Yeah, here it is. eb over mc. Okay, and collision integral acts on the function f of phi the same way it was defined before, integral over d phi prime f of phi minus f of phi prime with some kernel that completely determined by scatterings. Now again, we know how collision integral acts on first harmonics. So it acts on cosine phi. It gives minus 1 over tau transport cosine phi. It acts on sine phi. It gives again the same eigenmode with the same transport time. So it means that on this solution, in the linear space of functions that are either cosine or sine phi, the equation reads omega c d over d phi plus 1 over tau transport acting on function f of phi is equal to minus sorry, again, I'm writing e, but according to notes, there's no e, minus ev cosine phi, which means that that's a simple differential equation, and it has a solution f of phi is equal to minus v Fermi tau divided by 1 plus omega cyclotron square tau transport square cosine phi plus omega c tau transport sinus phi. Okay, let's check some obvious limits. So if magnetic field goes to 0, omega c goes to 0, f of phi goes into minus E V Fermi tau transport cosine phi, a familiar expression that we already seen many times. So only the first harmonic survives. This harmonics is an even function of phi, and conductivity in this case will be a diagonal matrix, diagonal tensor. So if electric field is in the x direction, current will flow in the x direction, will be no current flowing into the y direction. However, for finite value of magnetic field, we have an addition to the distribution function. It's also proportional to the first harmonics, it's sine phi, but this is an odd function of the angle. What it changes, so now let's compute current. So let's say that electric field has a only component in the x direction. So let's compute Jx and Jy. So current in the x direction is density of states, integral d phi over 2 pi minus E times V Fermi times cosine phi. That's the projection. That's the projection of velocity operator on the x direction times distribution function into that direction. We plug it all in, and we get E square nu V Fermi square divided by 2 tau transport 1 plus omega c square tau transport square times electric field. I guess we recovered something we seen not very long ago. However, if I can also compute transport currents or electric current in the y direction, and the only thing I need to change in this expression, minus E times V Fermi, and here I write sine phi, because I'm projecting my velocity operator on the direction y, f of phi. And lo and behold, I'm getting E square nu V Fermi square over 2 tau transport 1 plus Vc square tau transport square times omega c tau transport. So this is something which is proportional to the magnetic field. So we see that electric field is in the x direction, and I'm getting current which flows in x direction, but I also get the current that flows in the y direction. And this is whole component of the current. So this is a classical Hall effect. I'm getting current which flows in the direction which is transversal to the direction of the applied electric field. So if I present my current operator as a response at frequency omega, as a response to electric field, that now my sigma, the DC, okay, I wrote it as a function of frequency, okay, so that's not the DC, not necessarily DC, but my electric conductivity is now a matrix. So it's now a matrix in the XY space, yeah? So it has now a structure XX, XY, YX, and sigma YY. That's my matrix of electric conductivities. It has this tensor structure. And in particular, I have a current in the Y direction, which is sigma Y X E in the X direction. Now we have computed two components of this thing. we have computed here we have computed sigma yx, and there we computed sigma xx. So we know sigma xx and sigma yx. Now here I will make a claim that I don't need to compute anything else because I know that my spectrum was absolutely symmetrical, which means that sigma xx is equal to sigma yy. So elements they stand on the diagonal are equal because my spectrum is absolutely symmetric and there's no difference between x direction and y direction for this model. Moreover, I make a less trivial claim that sigma xy must be equal to minus sigma yx, and this response tensor must be antisymmetric. That's a less trivial point, but probably we will discuss it next time. But this is something that tells you that there are that we have a whole conductivity in the problem. Okay, let me just continue. This point is less trivial, but I don't need to assume anything. I can recompute everything again. I can go back to the equation. Let me put it this way. I can go back to the equation I solved. I can choose my electric field to be in y direction, compute everything from the very beginning, compute two remaining parts of the conductivity matrix, and then observe that this matrix is antisymmetric. And then that would be a natural conclusion of my calculation. However, I'm saying here that this is something way more general than this observation. I will always get that the whole component of the matrix are antisymmetric by violation of time reversal symmetry. So what we've, if you believe me with that, so that's what we found, that the matrix of whole conductivity will be sigma 0. This is the zero magnetic field, zero frequency, 1 plus omega c square tau transport square, and the following matrix 1 minus omega c tau, and 1. This is the matrix of electric conductivity, where sigma 0 is E square density of states V Fermi square over tau transport divided by 2. And this is also in this model is equal to n E square tau over m, where n is the density of electrons. Now I can invert this equation and say I found that the current as a vector is proportional to the product. So this is alpha, alpha, beta, beta, sum over beta. Or in matrix notation, J as a vector is equal to sigma as a tensor times E. I can invert this and say that electric field is equal to sigma minus 1 times J, or as it frequently called, rho times J, where rho is a matrix of resistivity. So this is electric resistivity. It's also matrix 2 by 2. And rho is equal to sigma 0 minus 1. Now, if I compute this matrix, I take matrix sigma and compute matrix rho, then matrix rho will be rho 0, 1 omega c tau minus omega c tau times 1, and rho 0 is just sigma 0 minus 1, which is m over n E squared tau transport. So what do we see from here? we see here that there is a component rho xy, also known as a Hall resistance, which is equal to P over NEC. I'm just checking myself. Right. And we see it from here. Yeah? So just it's rho 0 omega c tau, and it's equal to m over n e squared tau transport, omega c tau transport drops, and we get m over n e squared times omega c, but omega c, according to our definitions, omega c was defined just checking that I didn't make any mistake. Omega c, or defined it, EB over MC. So it's EB over MC, M drops, and I'm getting B over NEC, correct. So that's rho xy, and I compute rho xx, and rho xx happens to be rho 0. And what we see in this model, that this rho xx is independent of B, and rho xy is independent of disorder. So if I draw rho xx as a function of magnetic field, and within this model, it's a constant. And if I draw rho xy as a function of magnetic field in this model, it's a linear function. And the slope of this linear function, is proportional to 1 over NEC. So the only information it knows about this system is a concentration of the carriers. Of course, I made lots of simplifying assumptions on the way, but if we believe that the spectrum is parabolic, then essentially from this plot, I can extract the information about density of electrons. So density of carriers of electrons can be extracted, can be found experimentally from rho xy as a function of magnetic field, because this thing is independent of anything else. E is known, speed of light is known. You measure classic Hall resistivity, you extract carrier concentration. In this model, we also see that rho xx is absolutely independent of the magnetic field. Some of this is a result of simplifying approximation we have done in our model. And now, as you see, there's absolutely no quantum Hall here. We don't see any quantum Hall quantizations. That because there are some assumptions that we made that simplified our solution, but essentially some critical value of magnetic field where our treatment breaks down. So there's some assumptions of our fields to be sufficiently weak. What sufficiently weak means, we will discuss next time. But B is sufficiently small. Small, whatever that means, discuss next time. That's point number one. Point number two, sigma xy is equal to minus sigma yx, antisymmetric. Also to be discussed next time. That's no coincidence. That's something to be discussed. Finally, last point that I want to mention today is Einstein relation. We noticed last time when we talked about things without magnetic field that sigma electric conductivity was related to the density of states and diffusion constant for the case where diffusion constant was a constant. However, there is a diffusion current which is not necessarily parallel to the gradient of density. In this case, diffusion constant is not a constant, but a tensor or a matrix, which is formally defined as a correlation function of velocities, component I, component J, integral from 0 to infinity. See the discussion of the Kuba approach. So there is a diffusion matrix that describes the diffusion of particles, of the electrons, and can be formally computed via correlation functions of the velocities. Now, the statement about Einstein relation, and I'm not giving any proof, that this relation holds in the presence of the magnetic field, in which case sigma is just an antisymmetric matrix we have computed, and D is the diffusion matrix we have not computed, but we could have. And this relation holds in this case as well for all, and this relation holds for all temperatures, magnetic fields, and interaction, way beyond the validity of semiclassical kinetic theory I'm explaining, and only provided there is a such thing as a linear response to electric field and such a thing as normal diffusion. So if there is a process of normal diffusion which is quite general but not always exists, and there is a linear response to electric fields, so there is a linear regime of response of the current to electric field, which is also quite general but not always exist. But if these two things exist, they are intimately related to each other via Einstein relation, in which case both electric conductivity and diffusion matrix are tensors. Okay, but I think I described most of the classical magnetoconductivity. There are a couple of points that we will discuss next time, but that's more or less the overall picture of the classical magnetoconductivity, and probably you should look at this equation yourself for the matrix of sigma and see how we interpret the limits of small omega c and large omega c, and think about that. People, I'm done for today. If you have any questions that we want to discuss, please fire.
I have no questions.
Anybody else who wants to discuss anything or have questions or comments?
If you can please just remember to upload the recordings and the notes.
Okay, I will upload the recording. So there's this lecture and the one lecture before that.
Yes. And the notes as well of the.
And the notes as well, yes.
It will help. Thank you.
Okay, I will try to do all this. Okay, so since there are no more questions, I think that's a good point to stop and see you on, well, I guess there's a Passover vacation. So see you after the vacation then. Bye.
Every day. Bye.